Okay, so I want to introduce our first set of speakers, David Bock and Darren Adams from NCSA. Darren was actually our inaugural speaker when we first started the symposium series last November, so it's just nice to have him back. And David, we've been trying to get during the springtime, but he's had a teaching conflict at this time, so it's nice to be able to finally schedule him in and hear some of the work that the two of them have been doing with PI Antonio Ferrante at the University of Washington on his turbulence modeling. So there are parallel I/O aspects using HDF5 to this talk, and also visualization topics. And I remember when Darren presented, I think some time ago, about HDF5, how there was quite a conversation around this and how we ought to develop some user materials, tutorials, maybe a more in-depth webinar on HDF5. So that's something that we're still pursuing with Jay Alameda, our ESTEO lead. So with that, I want to thank David and Darren for taking the time to develop the presentation and join us today. So why don't you two go ahead and get started.
Okay, thanks, Nancy. As Nancy mentioned, I'm David Bock with Darren Adams here, and we're just going to give a brief overview of some of the work we've been doing with Antonio Ferrante at the University of Washington. It's been an ongoing project, running his simulation, working on his simulation, working on the I/O, working on the visualization. So we're going to kind of move into this, and I'm going to move somewhat quickly because I want to have plenty of time for questions at the end. Just very briefly, this is his science. I'm not going to get too far into this because this is his work, but he's looking at computational fluid flow at turbulent boundary layers. And I think what's interesting about his science is that he runs kind of a pre-simulation to calculate the inflow conditions into this direct numerical simulation running Navier-Stokes. So it kind of has multiple simulations running, which makes it a little bit more complicated for the aspect, again, of extracting the data, reading the data, writing the data into. But it's very interesting information here, very interesting science. In terms of the XSEDE project, I want to jump into kind of what we're doing here, what our goals were. Obviously, hours and storage on Kraken, Ranger. He's interested in trying to calculate, pretty high resolution simulations, one of the largest Reynolds number reported, and he's wanting to share this information with the community. And again, he's got some of his own goals, and we're going to kind of jump into that as well. So our specific ECSS goals that we kind of outlined from the beginning of this project is primarily focusing on what Darren's going to be working on first, and that's what he'll mention, a parallel I/O layer, which has been very beneficial to me, and that's why I'm excited about this project and want to talk about it, because it's one of the first examples where the visualization is working directly with the support staff here, using software that they've written, using software I've written on a real true collaborative project for the PI. So that's what I've been fortunate enough to work with Darren to use his library, which is nice. So he's going to talk about that. And then after that, I'll talk about, show you some examples of what I've done with the data, visualizing lambda 2, which is related to the vorticity in the science. So with that, we'll move into the software that Darren's written. So Darren?
Yeah, I'll just say a few words about the parallel I/O implementation. So this is part of the collaboration. Is the starting point for this code is a legacy Fortran collection of Fortran routines that they have been using, and their data analysis technique was to do a root gather and to write a native binary Fortran file. And then there was this very expensive post-processing step where I think they were actually processing that binary data into an ASCII file that worked with tecplot. So that was the starting point. So they clearly couldn't scale that, so they had issues on the running the simulations. And then on the analysis side, they had this expensive post-processing step and a real lack of portability of their data. So it's clear to me at the beginning that we needed to do parallel I/O. We needed a good portable data format, so HDF5 was a good choice for that starting point. But they would have a particular set of needs with their file structure, their the metadata from the runs and so forth. All these things are things that you think about when you're structuring an HDF5 file format for a project. And so in order to achieve those goals, I decided to write an I/O library that was also written in C rather than in the native Fortran language of their simulation, and then call it from their Fortran code, and then hopefully be able to reuse that same I/O library, since it's written in C, for visualization analysis. And so far we've had some success with that. So as Dave mentioned, he's able to use the same I/O library that they use in their simulation code to read the simulation data. And I believe his software that he has his own visualization software that he develops. It's written in C++. And there is also a visit reader that's been developed that uses library and it's also C++. So, and I think that's next slide actually. So I think, can you back up just for 1 second, Dave? See if I covered the, yeah. So then just to quickly summarize the simulation code side of the functionality. They need to do these large data dumps of their field variables. They needed to do those, I don't mention this on the slide, but they do this at regular time intervals, so it's a temporal evolution that they can capture. They also need to be able to dump double precision, full detailed field variable dumps for their restarts. And then they have a particle tracking where they do a different kind of I/O call to write out particle data. And finally, and maybe most importantly in the long run, is that we've encapsulated a metadata scheme that goes with the data that's stored, so that hopefully years from now, several grad students down the road, the PI will be able to use the data that they're generating now and have all the detailed information about how it was generated so that they can still do science. Okay, we can go next one. And then, yeah, just to finish off describing it, the other aspects, analysis and visualization, so reading of the data. We have a visit reader. Visit's a visualization tool developed at Lawrence Livermore. And they have a really nice, well-documented process for creating a reader. They have templates and things. It's really nice. If other people want to look into that, I was able to do that in just a few days, and that was really nice. A good, well-documented way to do that. And then finally, since it is an HDF5 file, you can access it directly, bypass my API and use it. And many other software packages support HDF5 access. And finally, we're also looking at some experimental interfaces to the library through SWIG for Python, Perl, and so forth.
So Darren's being kind of humble. The truth is he really cleaned things up quite a bit for, again, being able to access the data, read the data, write the data. So I've been using his API, and it made it a lot easier because before, as he was mentioning, as a graphics designer and scientific visualization expert, I'm going on working in Fortran code and running Fortran post-processors and trying to compute actual data when all of this really should have been done. And it's now being done in the library that Darren's written. So it's made our life a lot easier. So I simply use his reader to extract the data, and what we're looking at specifically is lambda 2, which, as many of you know, is related to vorticity using velocity tensors. And then I use that in a format that I use with a custom visualization system I've written over the years that I like to use to represent data. So I'm going to show you some of the work I've done in there, in the system I have, and what I've led up to final animations at the end of this. So the first thing we do is, as typical in visualization, is just kind of get a sense of what we're looking at with some slice planes. And so what you're seeing here on the left is lambda 2, and on the right is velocity magnitude. And what I wanted to point out here is during this visualization, it's really been kind of interesting because he's got these very small, the lambda 2 ends up being, with the larger data sizes, very small tube-like structures that you see. moving along the bottom of the plane. And so it's really hard to kind of isolate those. And so you can kind of see, this almost looks like noise at first when you run the slice plane. So really working hard on, when we try to represent this volumetrically, as you'll see in a minute, to isolate that. And so working with the collaborator, with the PI, trying to identify, the data he's looking at. So really working hard on the transfer functions themselves in my volume renderer. And so you can see I've got a Gaussian both in the hue as well as the alpha channel. And that allows us, when we volume render that, to start to see these structures. And again, we're just looking at what we saw using that color map from the previous slide, doing a volume render. With no lighting here, just getting a sense of trying to identify this. And so we're starting to see, again, these wispy tubular structures. And we're looking down the chamber here, and then a close-up on the side. And then I start to experiment using my system just with different kinds of visual styles, different representations. So we're looking here on the left. You see a top-down view of these lambda 2 structures that are going to be moving here in a minute. And then a 3/4 side view, trying to get kind of a halo look with both of these, where you can see the outside of the structure as well as inside. He had done previous visualizations like this a couple years ago, but he used isosurfaces with some collaborators. And I showed him the volume, and he was more interested in seeing the volume rendering because he could see more of the structure. So that's kind of what we chose to do here. And this data set that we're looking at is about 1536 by 512 by 192. It's about 600 megabytes worth of data. It's a scalar field, lambda 2.
Gigabyte?
Yeah, what did I say?
You said megabyte.
Yeah. And so what did I say?
Is it gig or meg?
Well, gig is all the time series.
Oh, okay.
This is just a single time step.
Okay.
Yeah, the full time series that we'll see in a minute is 600 gig. The data structure that the grid itself is actually generated from the data. So it's a shader that runs through the data set and generates the lines. And what you're seeing here, the grid lines, every 20th step or so. So what I want to show here is some of the final production runs we're working on now and adding some other things to these. But I've got 4 different animations that I've rendered recently. And what I've done is added lighting and shadows so you can get a reference of where these structures move along the bottom of the plane in the chamber. Increase the absorption coefficient so you can see more of the structure within the volume with multiple viewing. So what I'm going to do is, give me a minute, I'll bring these movies up. Hopefully you can see these. Everybody see those?
Yeah, looks good, David.
Okay. So what you're seeing is a top-down view of this movement. And again, this is the structure of lambda 2. It's about 300 time steps, so totally the total size of this data set that was read out from Darren's API is about 600 gigabytes. And so we're looking at a volume render of these from different angles. This is the side view, a 3/4 view of these structures moving. And then our final view is a view coming at the camera. So as if you're standing on the chamber floor with these structures coming towards you. We have a little bit. I'll run this one more time through so you can see it, and I'll conclude with some future work that we're going to be looking at.
David, I wonder if the PI has shared what kind of insights he was able to gain from this, and also kind of the use of tubes rather than streamlines or vectors or some other things I've seen used for turbulence. Seems a bit different. If you can comment on the utility of that.
Yeah, actually, that's a good question because this is right off the press. He hasn't even seen these yet. So this is a sneak preview. We haven't showed this to him yet.
Was he able to write out the results in a lot more detail because of the parallel I/O? Was that one of the goals for him?
Yeah, I think they had basically hit a wall because they would not have been able to do view these structures at higher resolutions with the approach that they were taking. And so there's a couple of other aspects of the project. They're transitioning to a 2D domain decomposition model so that they can scale even further. But now that this I/O subsystem is in place, you know, the development work they need to do for their 2D decomposition algorithm should be able to proceed and still use the same I/O mechanisms and still get the same visualization results with this software.
Just very quickly, we're just about out of the 20 minutes. I just wanted to show kind of where we're going and what we'd like to do with this. What I'd like to try to do is to integrate particles with this volume. And so what I'm going to show here is what I'm trying to accomplish here the next run of this. And this is from my system as well, but this is using a different data set. But I want to kind of give you a sense of what the particles would look like in this flow. So let me just show up one more movie here. And so what you're seeing, this is a previous simulation, not from Ferrante, just from previous research. Oh, do you see this?
Not yet.
Oh.
No, not yet.
Try this again. Start VLC, right? So this is an animation of particle flow using my renderer, and you can see that, you know, I'm both using kind of soft shaded particles as well as the streamlines. And so I'd like to kind of integrate this along with the lambda 2, just so we can, you know, again, get kind of relational representation between lambda 2 and velocity and so forth. And so that's kind of where we're heading next. So that leaves time for some questions.
Great, and there are some questions. Amit Charazia, rather than me rereading the questions, why don't you go ahead? I think there's not a lot of background noise, so go ahead and direct them to David.
All right. Hi, David. I'm just curious to know your Viz system. Are you running it on Big Iron machine or are you running it on workstation? You seem to mention shaders, so you're using GPUs or CPU?
Yeah, no, I'm running on my own workstation, and I use both software ray tracer that I've written as well as interactive GLSL shaders.
So obviously you probably tried to use Visit since you had written the reader for Visit. How does the volume rendering from Visit compare to your system? Seems like it may not be adequate. That's why using your system.
Yeah, that's probably the answer. You know, I think when he saw the output from what I was doing with the render, I've got a little more. I've got some more controls. It's more physically based. I can control absorption and scattering and things of that nature a little bit more than the volume render and Visit. So he was more pleased with what we were doing in that aspect. Yes. Yeah,
and I think that based on the results that he's been able to produce, I think that would be very difficult to achieve a lot of this functionality in Visit. But Visit is a good tool for the researchers to use to evaluate their data before we do any sort of really nice renderings like this.
Yeah, you know, my own system, again, it's been written over the years. I just have more control over it, so I can do more things than trying to fiddle around with Visit.
Certainly. Thank you.
Mm-hmm.
David, is your own system more specific to CFD and turbulence, or can it be applied to other areas as well?
Yes, it's a general visualization system and render.
So when you show this movement there, the movie, I mean, it looked like these caricatures are moving in the frame without any change.
Right.
Is that true, or is it just my illusion?
No, they're moving, and they're not, you wouldn't see the typical, vortices or hairpins vortices that you'd see. Yeah, that's what he expects to see.
Okay. Because it looked like it could be an artifact of just the camera moving.
No, there was no camera movement in those. The camera was stationary, and those were moving past the camera.
Right.
And again, if you look back on this slide, and it's been kind of difficult to find a good view because this is such a long, thin, narrow chamber. And these structures, the higher the data sets get, the tinier these structures get, and these structures are. And so it's kind of hard to see, particularly where the movements are. So trying to work hard on, what angle to look at. And you're only seeing one part of it as opposed to the entire chamber.
What are they looking at actually, David? What's it flow through what?
What's that?
What are they actually looking at? What type of flow?
So it's a turbulent flow. The bottom of the chamber is a boundary layer where they have a higher resolution, and that's where the turbulence effects are generated from the interaction with the boundary. So this is called a turbulent boundary layer simulation. So you have a flow from left to right in the visualizations that Dave showed, and where the vortices are forming is near that turbulent boundary layer. So we're looking at these. We're looking at these structures of a physical aspect of the fluid called vorticity, and in the vorticity plot, these structures form, and that's what they're trying to study.
Yeah, I was just wondering if it was, flow through a contained area or over a wing or.
It's within a chamber.
Yeah, it's just a flat boundary layer.
Okay. Yeah.
At the bottom of the chamber.
Yeah. Yeah. Great.
Yeah.
About how long have you been working with Antonino?
About a year, right? About over a year now.
About a year. Yeah. Yeah. Very good. Any other questions from the group for David or Darren? Great, thank you very much for a nice enlightening talk. Nice length, very direct. Described exactly what the type of work that you did in the ECSS project. Very nice.
Okay, thank you.
Yep. Thank you very much.